Excuse me. So today we're going to do the last in our series for the webinar series on irrigation professional development. This one's on microirrigation, or sometimes called trickle or drip irrigation. So I'm going to try to go through this morning just some of the advantages and disadvantages of this type of irrigation, as well as some of the equipment that would be used. And then we'll talk about how to schedule, and that's a little challenging in some cases, but we'll try to give it a shot here and do the best we can. If you have any questions, you can type me in the chat box or raise your hand, and I may not get to your question right away if I don't see it, but let me know if you got a question, and we'll try to backtrack and answer them as we go along. All right. Now I just got to get to cooperate. There we go. So what is micro or irrigation? Basically, it's a method of metering small amounts of water out slowly into the root area, or root zone area, either from the soil surface or directly into the root zone, and that's sometimes called subsurface irrigation, through a network of valves, pipes, tubing, and emitters. So the pictures on the left or right here, the top one's just an emitter that you might use in a pot or at a single source point versus a drip line, which you'd use on a row of crops. So when's the start? Actually, the early research started in Germany in 1860, and I'm not sure what they were using for piping at that point, but the idea was to meter out water slowly to the crops. It really started to take off in the 1940s in greenhouses in England, and with the development of plastic tubing in the 50s, then it really took off, especially in arid countries like Israel. And Israel has really been a leader in the development of drip irrigation. So some of the major companies are from Israel. So the idea is, as I said, is to meter it out water slowly and frequently into the soil. And we're using a low pressure distribution system. These systems typically run at about 10 psi, although they can be up to 60 psi, although that's less common. Might be more common if you're doing a large field, very large field. In most cases, it's, at least in Wisconsin, it's going to be small areas. And we've got some kind of special flow outlets, and we're going to talk about the emitter part of it and show you what they look like and how they work. So it is often called drip, or bubblers is another name, but I haven't heard that here as much, or trickle irrigation, and it can also be used as subsurface irrigation. And it can be, we can deliver it to an individual plant. So if you're in an orchard, that's often, or grapes, that's often done, is where it's delivered, you know, within the root zone of a single plant, or it can be a row of plants. And it's very easy to put together. During our workshop this summer, we'll try to have you guys put a simple system together. So the concept is that we're excuse me, we're gonna wet the soil near the plant. So we're basically just trying to get the root zone wetted. We don't care anything about beyond that, because anything beyond that's kind of a wasted use of our water. So that's the basic concept. And it's typically on high value crops. You wouldn't see it in Wisconsin on field corn, but basically it's fruits, nuts, grapes, you know, vineyard crops, strawberries, that's a big one, flowers and vegetables. It does have water, very high water efficiency use, about 90%, although it can vary a little bit. And that has to do with the how even it puts the water out throughout the emitter strip. and there is a little variation because you're going to have pressure drop down the drip line. But the big advantage to this is going to be use of water. And basically, because we're not wetting as much area, we can save up to about 50% in water. Although, you know, it depends on the crop and how it's laid out and that kind of stuff. But basically, we're not going to water areas where there's no roots. So here's some examples. On the left here, we've got an orchard. We have a little micro sprinkler. It's basically just wetting you know, the diameter where we'd expect the root zone to be. In the lower right, we've got what we typically probably see here in Wisconsin. And this is actually set up in two ways. Let me see if I can get my pointer out here. So if you, come on, pointer. There we go. Okay. So this you can see, you got a row here right next to the crop, and you got a row here right next to the crop, versus over here, it's down the middle between two crops, and then the next one is down between the two crops. So that's that's another way to do it. If you have a crop that has a large root zone that would intersect, you can sometimes just do it between the rows instead of right along the row. In the upper picture here, we've got subsurface irrigation, and I've got the arrows where the pipes are in the ground. So this is corn. We do it every other row, and you know, what we're counting on is that early in the season, when we first plant the crop, we're going to have enough water to get it to germinate, and then after that, the roots would climb down into that wetted zone to get their water. We can use it on nurseries, potted plants. That's a very common use of it. And here's a benchtop in a greenhouse where you have these little your main excuse me, your main lines running down here, and you have these little tubes with an emitter on the end going to each individual pot. And you'd see the similar thing out here, except here we might have, this is a tube, and you have an emitter at the spacing you want the pots at. So water distribution, the big advantage is over sprinkler. Sprinkler, we're going to wet the whole area, whereas with drip irrigation, we can wet just the root ball, basically. And here's what the alternate row subsurface would look like. You'd have a wetted area between, and you'd expect most of the roots would end up in this area. So what are some of the advantages? Basically, reduced evaporation. We're going to minimize percolation or leaching. And we're going to have consistent root zone moisture. Now, you have to be careful with this method because we can actually get too much water down there and cause root diseases. But if it's done right, we're going to put a little water in. We're going to let it dry out a little bit, and then we'll put a little more in. So plants never in stress. Generally, depends on what you're comparing to. The labor requirements are lower, and you have higher water efficiency than, say, a sprinkler system. And weeds are more easily controlled. Actually, if you have it where something like this, where you have it right next to the plant, this area in the middle here is going to be dry, and it's going to be really hard for plants to germinate unless you get some rainfall too, or weeds to germinate. So that can be an advantage from a weed control standpoint. You also have some advantages versus getting wetted leaf areas. We can reduce our fungal diseases or bacteria diseases from splashing water up from the soil onto plants because we basically have a dry environment unless we get rainfall. Low water applications rates eliminate runoff, providing it's managed properly. And we can maximize the use of chemical applications like doing chemigation or fertilization through it. We can do one is we can meter it out as the plant's going to use it. and the other is we can reduce the amount that might get into the groundwater because we're going to meter it out all through the season instead of conventional agriculture. You put it on, once or twice during the growing season, and it's there for the elements to do what you want with it. Some of the disadvantage: high cost. Its estimated cost to do an acre of land is about $1,000 to $1,200. Now, we talked about center pivot irrigation previously, and that was about $1,000 an acre as well. The challenge with this is $1,000 that's only going to last 1 to maybe 3 or 4 years, and then it gets replaced. Now, subsurface will last a little longer, but generally you're going to end up replacing that more often. So that's a recurring cost versus kind of a one-time every 20, 30 years. We can have problems with emitters plugging with a particulate matter, or we can get bacteria growth or algae growth in the tubes, or it can be chemicals. Basically, we can get drying of mineralization on the emitters that plug them. So we need a good filtration system with this, and that's going to add some cost. But it's not insurmountable. So the other disadvantage is it may restrict the area, the plant root zone, or the plant roots may be restricted just to that wetted area if we're in a very arid climate or arid soil, because it's not going to have enough water for it to chase outside of that. So that can be a problem. They kind of get root bound or not have enough roots to hold up the plant. So the dry soil between emitters, it's an advantage for weeds, but it's also a disadvantage for dust and wind erosion. Although if we've got a good crop on it, that should help take care of that. And we may need more highly skilled labor to operate and maintain this, because if you've got a leak, if you're doing subsurface and you got a leak underground, it takes a little skill and problem solving to try to figure out where the leak is and how to manage that. It can be expensive to implement on a large scale, although out west they're doing it. I've seen articles where they're doing it on a large scale on onions in Idaho. The challenge here is you've got to have it somewhat automated to put your drip lines down when you're planting to reduce that labor. And if it's a permanent system, say like a subsurface, we may have to drain that system so it doesn't freeze and burst pipes and stuff for cold weather. When we're looking at a site to do this, we need to look at what the water system source is, both capacity and pressure, and the level of filtration we're going to need. So if it's surface water, we're going to need a little more filtration to get potential algae out than we may need for a well situation. The texture of the soil will have an effect, mainly on the wetted area and how the water will percolate into the soil and the shape of that wetted area. And we'll show a little bit about this in a minute. And then we need to know potential of the climate and our potential ET and topography. If we've got a rural rolling field, that may affect how we lay out a system so that we don't have a lot of pressure differences because of elevation. Or we're going to need to use pressure compensating emitters to take that into account, and that may require higher pressure to do that. So here's looking at the different soil types. In Wisconsin, we tend to just irrigate sandy soils, and the biggest thing I want you to see is the shape of the wetted pattern. In sand, that water tends to go straight down, doesn't spread out as much, So 1 to 3 feet is what the literature says. You know, and it's going to depend on whether it's sand or more of a loamy sand as to how much that'll spread out. But typically you're going to get something that's more looks like a cylinder versus if we get you know, a loam or something, it's going to spread out a little more, maybe look like more of a half a beach ball because it'll spread out. And then if we get clay, which has a low percolation rate, it may just kind of sit on like a pancake, so it may not go very deep. And especially if we have, you know, a plow layer or impermeable layer, hard pan, that can affect how far down that can go as well. So those are all issues that we need to take into account when we're looking at the site and how we're going to lay a system out, or what kind of water flow rates we're going to use. So as much as possible for elevation changes, we'd like to follow the contours, though it's not always possible. But that can help reduce variation along the drip line because of topography. And the other thing is when we put in a air or vacuum relief line at the highest point, so that it helps the system drain down better. So here's kind of a typical layout with a pattern. So over here we have our water source. It can be well or groundwater. We're going to pump that water up through. This is NRV is non-return valve. So that's or anti-siphon. If something happens in the system, we don't want the water to siphon back through. We've got a cyclone filter here to filter out heavy particles. Then we've got a sand filter here to get most of the bulk of any sediment or bacteria, you know, algae or anything like that out. And then we've got a screen filter here, and that basically works best against inorganics, so little particles in the system. Then we'd have a main line that may go to several systems. Then we'd have a sublateral. We'd have a valve in here so we can control it. And then we have our laterals going off to our crops. These lines usually go out and are dead-ended, so they're either just folded over or they may have a valve on the end. And we want to be able to flush these. So, you know, here's a area where we have a valve that where we can just open it up and flush through, especially first part of the season or during the season to flush things out. And then here looks like they've set up with a emitter basically at each plant. So those are components. So we're going to we'll walk through each of these parts in a little more detail here. So water source, well is going to be our cleanest. If we use surface water, that may require some extra filtration. And basically it's because of small emitter orifices, plug very easily. And I'm not sure why I wrote pressure required. I'll have to think about that. Maybe I got a phone call in the middle of that one. But anyway, pressure, yeah, and we need to have pressure. So we need anywhere from 10 to 60 psi to run one of these systems. You actually can do them on gravity too. You don't necessarily need a pump. In third world nations, often they'll put a little stand up with a tank on it, and with a small system they can meter the water on. A backflush preventer, basically it's prevent water from returning to the valve, and it's especially important if we're doing chemigation. So if we're putting out herbicides, pesticides, fertilizers through the drip irrigation, we don't want any of that stuff to have a chance to get back into the water system. Filtration. So we're going to spend a little time on this because this is really important. So we want to remove any suspended solids in there, so that on the organic side it can be algae, moss, worms, bug larvae, you name it. If it can get in the water, we need to get it out. And then the inorganic, so sands, silt particles, mineralizations, minerals that precipitate out. So they can be an issue. So we need a minimum, and when you buy a drip irrigation system, it usually will state what the minimum requirement is for filtration. But typically 120 is the minimum, but more is better. Although more causes some issues with some other issues with filtering and back pressure and stuff. But 120 to 150 is typically the minimum range. There are some that we're going to require up to 200 mesh. So we'll look at that in a little more detail. So we can have a sand filter as one job. It does a great job of removing both organic and inorganic materials. The amount of filtration has to do with the particle size or media size we're using in the filter. They can be set up to automatically back flush and clean themselves. And they can filter to the equivalent of a 200 mesh with the smallest media size. So here's what a typical one would look like, and typically we're going to have two in tandem, so that if we have to backflush one, we'll backflush one while the other is still running. And for large systems, we can have a number of these in a row. But so just to kind of show you, see if I can pick all the pieces out of this. So here's my line coming in with my water coming into this. And it actually, I don't think it comes in here because this is my backflush out the top. But this water is actually coming around and coming into the top of these tanks and down through, and then it's coming out. Oh, maybe this is the outlet here, and we can't see the inlet. I think that's what's going on. I think the inlet might be right in here. So this other pipe, this lay flat pipe on the ground here, that's our flush. So when it flushes, it goes out. In this case, on the ground. So the guts of it, you've got media inside this tank. The normal pattern is the water comes through and through the media and down through and out the bottom. This is basically what they use in swimming pools, so if you're not familiar with that. To backflush it, we bring the water back in and up through these little nozzles which aggregate or mix up the media. But we bring that in at such a speed that doesn't push the media out, backflush it out, but any light particles are going to basically backflush out of this to clean it. So this can be set up on if you've got some automated valves and stuff, this can be set up to clean automatically. Next type of filter we're going to cover is a screen, and this can be an open screen. Where we basically just have a screen and we're going to run the water over it and let gravity flow through the screen. This is particularly good for really dirty water conditions because they can be kind of self-cleaning as time goes on. The other kind that's with small systems that's more prevalent is a pressure screen where it's basically in the line. It's got this cartridge in it. With a certain mesh screen, so it's going to fit in here. So the water is actually going to come in up to the outside into the screen and then down and out to the drip line. So it works very well with organic or particulate matter to get that out. The last type of filter we're going to talk about is a centrifugal type. So in this case, the water is going to come in. It's going to run in a circular pattern down through. The heavier particles will get thrown to the outside, and settle out, and the main part of the water will run through and out the filter. So this is kind of what the one would look like in the field. So this is the centrifugal separator. Here are my screens here, my pressure screen separators or filters here. So just to give you an idea of what they would look like. So it's really good at getting heavier than water particles out. It won't get light particles out. So, you know, sand, silt, that kind of particles will get thrown out on one of these separators. Let's get into kind of the piping systems. We'll talk about the main line. One of the sizing things for main line is that we want to keep our water speed to 5 feet per second. And this is mainly because if you get above 7.5 feet per second, our water velocity head increases and our pressure drop will increase rapidly after that. So trying to keep it to 5, design it to 5 feet per second, and then if you expand the system, you've got a little leeway. You can go as high as 7.5 feet per second. These pipes can be PVC, lay flat, which is the blue stuff down here, roll up flat. It can be polytubing, hose, you know, garden hose type. All of those can be used. So here's a picture on the right here, shows a lay flat tubing, or maybe it's a heavier tubing, but we've got our lines for our laterals going right into that large line. And over on the side here, it's showing, so we got a lay flat line, and we've got these little fittings that just plug right into there. This one here in the center has a valve on it, so you could shut that off, but just some different methods of doing that. And that's the same for sublines too. And then we have the lateral lines. I think I've got a picture here coming up. It'll be there's two types. One's called lay flat. They're 5/8 or 7/8 in diameter, so it depends on your length of run which one would be the best. Variety of wall thicknesses, and that kind of depends on how long it's going to be out there. You know, 5 mils is kind of a throwaway. 1 year, you're done with it. As you get into the maybe 8 to 10, you might use it 2 or 3 seasons. So, and it depends how it's being used, whether it's perennial crop or under plastic. Plastic will help protect it a little bit. And then the emitter spacing. The emitter spacing can be anywhere from 4 to 24 inches apart. You know, it's typical on a lay flat tube with discharge rates of anywhere from 2/10 of a gallon per hour to 2 gallons per hour. So there's actually a wide range of emitter things. Now, the flow rates are either given by the emitter, the ratings on these tubes, because you have to buy them. You buy them for the flow rates you want. You can't change it once you buy it. But typically they're in gallons per hour per 100 feet, or in some cases by emitter. But if you do it by 100 feet, that makes it fairly easy to do your calculations later on. The maximum length is going to depend on the flow rate, the diameter, and the topography you've got. And the operating pressures can be anywhere from 6 to 25 psi. And that largely has to do with the length of the run we're going to use for that. So here's a pictorial. So here's an emitter I got circled down here. So this is the emitter. And you can see that there's something embossed in that. Well, behind that is these. This is actually the emitter, and I like this picture on the right here because this is the back side that faces the inside of the tube, and this is what's up against the wall of the tube. So the water comes up through this little opening here. This may be easier to see, up through the opening here, and then it has to wind its way through this little maze here before it gets to where would go out through the opening in the pipe to let the water out. So these little bars in here cause eddy currents and a high pressure drop, so that's what controls the flow rate through these. So they're fixed rates, and these are mounted on the inside of the pipe. You buy it already mounted, and you just unwind it and use it. So here's an example of what the specifications might be. Here's my flow rate based on the pressure at the emitter. So it can vary a little bit. This side one I don't think is pressure compensating. We've got different spacings of the emitters here. And then over on the far right here is my gallons per minute. So if you times that by 60, you'd have it in gallons per hour. And so these are, this first column, these are all 0.16 per emitter, and bottom ones here 0.3 gallons per hour per emitter. So it depends on what your need as to which you'd buy. You know, the disadvantage, if you buy one that's a little small, you just have to run the system longer hours to get the same amount of water. And sometimes that's an advantage. So here this chart shows the PSI ratings, and this is the gallons per hour per emitter, I believe. And this is the, depends on the spacing and the maximum length of run. So at lower flow rates, you can see each of these. At lower flow rates, you can go further distance than at a little higher flow rate. So this would be something that would be specified by the company that's supplying the tubing to figure out what your maximum run might be. And this is assuming 8.5 psi at the end of the lateral. So at the beginning, it's going to be higher than that, depending on the length of run. And no slope on this. So, and then we have how many gallons a minute we can get through different pipe sizes, and this is based on that maximum velocity. So if we've got a half-inch pipe, we're only going to look at just a little under 5 gallons a minute, and we're going to have a pressure drop of 7.7 psi per 100 feet. So just to give you an idea of the length of run, so you're limited in some cases by the diameter of the pipe as to how far you can run a particular lateral and the pressure you're running. So lay flat, the maximum you're going to go is about 25 psi. This rating here, this is going to be for a hard poly tube with emitters, and we're going to show that next. That can go a longer distance. So some fittings that would be used on tape type. Basically, your tape hose would slide over this and under this fitting, and then the fitting is turned and clamps down onto the tape to hold it. One like this without, that's meant to go into a poly tube where it just stretches over top of the harder poly tube versus a tape. This one here, this is one that would go for a lateral, so you punch a little hole in your submain or your main, and this just pushes in, and then this side would have your tape on it. Here's one. This is a mending one or joint. Here's one to go to a threaded line. So all different types depending on what your needs are. The next type is it's basically a PVC tube. It's a hard tube or it doesn't lay flat. You can see this has got a little enlarged section. That's where the emitter is. They're put in there as the pipe is molded. So it's thicker walled. It's better for permaculture. So orchard grapevines, etc. Something that will be put out there and they expect it to be used for a long period of time. If you're going to use them for short periods of time, the advantage of them is they don't kink as easily. The lay flat, when you try to roll them up, they tend to kink, and the kinks are where you get holes. So that's an advantage that way. So emitter spacing, a wide range of emitter spacings, more toward permaculture, and a wide range of flow rates in gallons per hour, and higher pressures. So this is one thing, that other chart I showed you, I probably should have moved it down. So they can go longer distances per run, although it depends on, again, flow rate, diameter, and topography of the area that you're dealing with. And this would be the type of tube that would be used for subsurface irrigation because it's not going to crush when you backfill soil around it. Types of fittings, there's a number of types up on the top, these brown ones. Those, you're just going to push the hose over top and it's going to hold it in place. This is another type where you push the hose in. It's actually got inside there. In the inside, it's got a little indent, something like this. So it'll have one in each side. And when you push the hose in, it kind of forms around that and makes a seal. Just different designs, and then the end, to plug the end, you can either use an end cap on it, or you just take these little devices and kink the end so you get a fold and it folds over. Typically with drip irrigation, if we've got a little weeping, we're not too worried about it, especially if it's in the field. Now, sometimes some crops, like pick on strawberries, or maybe cranberries, although they tend to use solid set irrigation, but you could use for frost protection or cooling with these little micro sprinklers. And they're also used for orchards. So, they come in some fancy patterns here, depending on what you're trying to do. So here's one that looks like a little spinner here, or a spray nozzle, puts out a fan of water. Here's one that is putting out, looks like 5 or 6 different sprays of water for watering. So these are used a lot in landscape irrigation, but they can be used for frost protection. And here's a different type. This one's intended for orchards, but you could use it in strawberries for frost protection. This one has a 340-degree pattern. So basically, you've got a wedge out. The idea is you've got a wedge out, and here's where the tree is. So to go around both sides of the tree is kind of the way they've designed these. And this one, this particular model, they've got a 10-degree downward trajectory, basically to help fight wind. Now that's going to reduce the coverage area, but these do have quite a bit of coverage area, and that's on a 6-inch riser. So they do throw the water out quite far and operate at a pressure of 15 to 40 psi. So the higher pressure is going to throw the water out further. So just an example. Now, we talked about topography and what happens there. Well, in that case, we'd want to use a pressure compensating emitter. And you can see that these have very little change. It's pretty flat as far as outcome based on different PSI. So as long as you stay above that 15 PSI mark, they're going to be a fairly flat pattern. So these are typically used with the drip tubing versus the flat tape type tubing. But here shows another one too. Here again, these are fairly flat. So some optional equipment that we might use with drip irrigation or trickle is some kind of controller. So these can be a time clock, or it can be soil moisture controlled to turn on and off the water. And actually some controllers, for lawns especially, they have moisture sensors to sense whether it's raining or not. So they're not irrigating when it's raining. So these can be turned off by time or water volume or clock time. It just depends on the system. But here's a simple one that might be used for a small farm or a landscape type thing, where you do simple program things in. Flow meters can be very handy, especially if you put them on different zones, and it can help you detect leaks. So you put the system together, you start it up, make sure everything's working, and you look at the flow rate. So you know what the flow rate is. At some time down the line, if you see the flow is less, then you know you possibly have plugged emitters. On the other hand, if it's greater, then you know you probably have a leak. So it's one of those tools in the line that can help you troubleshoot. It also tells you how much water you're using, per year per irrigation event. Chemigation, I've alluded to this earlier. We can inject fertilizers or herbicides, pesticides into the water. Basically, if it's herbicides or pesticides, it's typically systemic type stuff, because with herbicides, you're not going to have a very big wetted pattern. But fertilizers is the biggest one that they would put into the system and deliver with the drip irrigation. One of the things, if I do use chemigation, we want to make sure that that product is flushed completely out of the drip line before I turn it off. Otherwise, that can cause fertilizer left in the line can cause bacteria growth, or it can cause crusting or plugging of the emitters as the salts dry at the emitter. So that can be an issue. So here, a simple, this would be for like a home garden or whatever, a small scale situation, just kind of we've got our water source over here. We're going to have a vacuum breaker. That's basically our non-return valve. We're going to have a pressure regulator to reduce the pressure coming out of the system. Got a little adapter here. We've got our drip filter. So there's a pressure filter on this one. And then a adapter to take my polytube and convert it from a threaded fitting to my polytube fitting. The one on the right's the same thing, except I've put a timer in the line as part of that. So that can be a very simple system. So some maintenance, we need to flush the lines on occasion to get any particulate matter out that made it through the filters, so that we don't get, we have longer life on it. So once or twice a year typically is going to be enough. We need to clean our filters. So that's going to be probably a weekly or bi-weekly thing to clean the filters. And we do have to watch for plugged emitters. And if they do become plugged, we have to be able to try to clean them. So sometimes it's going to be roots trying to feed into there. Sometimes it's minerals. So we may even have to put a herbicide out there to kill the roots or burn the roots off, or some kind of chlorine or acid, which will either burn the roots off or help with dissolving the minerals and flushing them out of the system. And I already mentioned chemigation, trying to flush that out. One of the biggest challenges with permaculture and any kind of irrigation, but especially drip irrigation, is control of salts in the soils. A lot of crops are very susceptible to salt buildup in the soil. So we either need to flush the soil, basically create a leaching event to move the salts down through the soil profile, or do crop rotation to help with that. So one of the things in the design of our system is to know what the rooting habits are of the crop we're trying to feed. So here's a pictorial. This is out of the USDA manual on irrigation. So, you know, you can go from corn, which has a very large root ball, you know, to something like a spinach or strawberries, which is pretty small and not very deep. So we've got to, you know, look at the type of crop we're growing, to look at, one, the number of emitter lines we might need, and based on the soil type, the shape of the wetted area and the location of those emitters. If we're doing under mulch, you know, plastic mulch type thing, we often will put a drip line there, and we need to look at where the drip line goes versus where we're going to plant, basically so that we don't come through and take our drip line out in the process of trying to plant. So typically these the drip line's going to be offset if you're planting down the center, or it might be down the center if you're planting double row in the mulch. The emitter spacing will also have to do with the soil and the wetted area we're trying to look at. So it also has to do with the amount of time we run the system and how kind of a management issue. So one thing to realize is that I'm going over on the right here with this picture, tries to show you the number of minutes of irrigation and how far that water is going to travel. So this has an effect on knowing the depth of the root ball or the root zone and how far that water is going to move or how fast that water is going to move down through it. So the temptation sometimes for people is to water a little bit multiple times a day. Well, if you do that, you may end up with you know, a very wet area up in here for crops that really has a much can withstand a much deeper root ball. So we need to understand the size of that root ball and how fast the water is going to move down through that soil profile to match that to our irrigation timing for that. The other thing is the emitter spacing. So we have a close spacing, which is typically used on row crops. We can go with a much shorter time than if we have a much wider spacing and we try to go with a shorter time. We end up with dry pockets or inadequately watered areas within that row, versus if we go to that wider spacing and do a longer run time, then the water is going to fill in more evenly. So those are things to consider when we're doing it. So typically, my thought is, you know, if you've got a row crop, you probably want those fairly close together, maybe no more than 12 inches apart. But that's going to also depend on the soil type. You can get away with, if you've got a loamy soil, you can get away with wider spacings on that, because there is a little bit of cost increase based on the number of emitters in a pipe. So let's get into the water management side of this. So there's a couple different ways we can do this. We can do a soil moisture-based scheduling. So basically we put in some soil moisture sensors in the soil to monitor how wet or dry that soil is. And then we can use the checkbook method. And there's limitations on both of these, because even using the checkbook method with drip irrigation, we're not wetting the whole profile, so that there's some unknown or some challenges there in understanding how that water is percolating into the soil and how big a pattern it's making. So basically we can overcome some of these limitations by using both. And the other question is, was raised is plastic mulch. The assumption is that if you have plastic mulch, you'll use less water, and that's probably true to a certain extent, but it's usually not enough to affect our water use. Now, it would provide less drying near the surface because you're going to get some evaporation out of the soil. It'll condense on the bottom of the plastic and keep the soil wetted up near the top a little better. But it also can be a detriment because as a grower, we may not be able to tell how wet the soil is underneath that plastic. That's how wet the trickle irrigation has made that. So using a soil moisture sensor is a good way to help understand, one, how big the water pattern is and how far it's going. So how are we going to do this? So one method we're going to use in Wisconsin, we can still use our canopy coverage. That's a good estimate. Although if we have trellis crops like a tomato plant, it may underestimate water use. So that's going to be some experience. I haven't been able to find anything that definitively gives some recommendations on trellis crops, but they did note that they will tend to underestimate water use, especially when the crop is mature. The other is effective rainfall. With sprinkler irrigation, we use about 1/4 inch. We don't count with drip irrigation. The recommendation is 1/10 of an inch of water. It doesn't count. I'm not sure, and it could be that this is because of the region that came out of, but so that's something else to look at as to whether that's a good number. But some variation. Then we've got non-uniformity factors. So that variation is water distribution along the drip tape, and basically it's 80 to 90%. So you know, it's kind of one of those estimated factors. If you really want to go out there and figure it out, you can go out and take your drip tape and put up some cups under the drip tape, you know, along the length of the drip tape, and try to figure out what the distribution is along the drip tape to figure out what that number, a better educated guess on what that number should be. But typically, I think if you're on a fairly level field, you could probably go with a 10% adder. If you've got some rolling topography, you might want to go with a 20% adder. And then the allowable depletion. So how much we're going to allow the water the plant water use to pull down the water in the soil profile before we rewater. And we're typically not going to let it go down to 50% like we do with most crops. The kind of recommendation is about 25%, because that's one of the advantages of this method, is that you can water more often. One, because you're going to set it up for the whole field possibly, although that depends on how much water you have available. But you're going to put a little water on more of the time to reduce, basically to reduce the possibility of leaching events especially. Because the water is going to go in a smaller area, so we do have some concerns of that regard, that we're only putting it on at one point, and it's going to kind of flow out, you know, capillary action, flow out from there into kind of a cylinder-shaped area, but we're putting it all in one spot, so we could have a leaching event. So if we reduce that water amount, and then the recommended application is a 1/2 inch or less maximum, and it's probably going to be less than that most of the time, but that would be the major factor, and that's going to be on a fairly deep-rooted crop most likely. So smaller amounts more often, but we do risk, if we do too small amounts, the risk that we're limiting root growth to just that wetted area. Now typically in Wisconsin, because we're not that arid, that's probably not an issue, unless we're in a drought year, but that can be a factor. So our canopy cover, that's one of the things we can use with our irrigation scheduling, and we went over this previously, but you look at what the maximum canopy width is here and the row width, and you put it in the formula. So you get row width over over canopy width. Oops, I got that formula upside down. It must have been too late when I was doing this. So we're going to flip this formula around here. So it should be the canopy width over the row width. So that's going to give us a percentage, something less than 1, that we're going to use. And then we're going to take that and we're going to go into this. This is out of the A3600 publication, the irrigation management in Wisconsin, and say we had 0.22 potential irrigation or potential ET, and we've got say a 60% cover over here. So we'd go down here and we'd find the adjusted number is going to be 0.19. So that's how we'd use that to get that. So when we're applying this to determine that the ET would be, we'd basically go do what I just did. We'd look up those numbers. Then we need to use this non-uniformity number. So that's going to be 1 to 1.1 to 1.2. We can take that and convert that to quantity of water. And this is going to help us decide how much water we need to put on. So we're going to take that ET applied. So that's this number here. After we take our adjusted ET, we're going to times it by the uniformity factor. So this is going to be like the 1.1, and we'll get a number there. And we're going to times that by the gallons per acre inch times the wetted area to get the gallons used. So this number here basically adjusts it for the amount of area that we're actually irrigating, because we don't care about the rest of it. So we're just irrigating the root zone. So we're assuming that the root area is equal to the canopy cover. And most plants, that's a pretty good estimate. So here's an example. Here's my 2.2. I did 40% cover here, 90% uniformity. So if we go to the table back here, 2.2, we go over to 40%, come down. Here's my 1.15. Then we're going to take that and we're going to times that by the 1.1 for our 90% uniformity. We're going to get 1.65. And then we're going to take that, we're going to convert that into inches. Here's my percent cover again. And we're going to need 1,792 gallons of water per acre per day to replace the ET for that amount of ET. Then the other thing is to look at the flow rate, so we can figure out what we want to do is calculate the time it takes for our system. So we need to determine the drip rate. So the number of drip lines times the rate per 100 feet to get a per 100 gallons per 100 foot. We need to know the linear feet of row. So we're going to take our acres, our square acres of field divided by the row width to get the linear length for an acre of field, and it might be something less than that if we're only doing part acres, but we're going to do it on a per acre basis in this case. And then we're going to take our flow quantity coming from our drip line and times it by the linear length on a per 100 foot basis to get the total quantity of water that we can supply in that line on a per acre per hour basis. Because these drip lines here, so I should have this should be gallons per hour. I'll have to fix that before I post it. And then we're going to take this formula. We're going to take the ET applied. So that's my 1,792 gallons times my water. So that's going to put it into gallons per acre We're going to divide it by this total quantity of water coming from our drip tape, and that's going to give us our run time. So here's an example. So if I got tomatoes 36-inch spacing, 2 drip lines at 20 gallons per hour each, or 20 gallons per hour total, I'm sorry. So I've got my 2 drip lines times 10 gallons per hour per 100 foot. It's going to give me 20 gallons per hour per 100 foot. My linear length, I'm going to take my square footage of my acres, divided by 3. I'm going to have 14,520 linear feet of row in that acre of land. I'm going to take my 20 gallons per 100 feet times my linear foot. I'm going to divide it by 100 to get the linear foot in a per 100-foot basis. And I'm going to have 2,904 gallons per hour per acre of water available. So if I put that in here, I'm going to find I've got to irrigate for 0.62 hours or 38 minutes per day to replace the water based on that ET. So the next question becomes how much ET can I tolerate before irrigating? And you know, typically it's going to be about 25%, so that's my allowable depletion. But basically, the way you can calculate this out is you took your effective root depth, your water holding capacity of the soil, my fraction of the soil that's wetted, so that's we're going to have to calculate that out. And that's going to give us the maximum inches of ET between irrigation events, or maybe not between irrigation events, but ET before I want to irrigate, I guess between irrigation events. So my fraction of the volume of the soil will depend on the soil type. We're going to use an example here of 30-inch rows, 18-inch rooting depth, and 1.8 inches of water per foot in the soil holding capacity with a loamy sand soil. So if I look at my my patterns here, loamy sand is right in here. So I think I picked a 1 or 2 inch diameter. Let's see what I picked here. So I'm assuming a 24-inch wetted diameter. So I'm going to assume that that's a cylinder in the soil under the emitter. So the formula for a cylinder is pi times d divided by 2, so the radius squared, so that's the area of a circle, times the rooting depth. So pi is 22/7, that's an easy number instead of otherwise it's 3.14, da 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 da. So if I put that in, I'm going to end up with 8,146 cubic inches of soil. Then I need to calculate out the total volume of soil that might be in that area. So I've got my wetted diameter times my rooting depth times the width, the row width. So that's basically a cylinder or a cube. So I got 24 times 18 times 30. I got 1,209.60 cubic inches. If I put that into a formula, I find that I got 63% wetted volume out of all that soil. So then I can go through here and use that in my formula. So I got my effective rooting depth is 18 inches. I'm going to convert that to feet. I get my soil holding capacity is 1.8 inches per foot. My wetted volume, fraction wetted, and my allowable depletion, I'm going to look at 25%. So that brings up 0.43 inches of crop ET. Basically, that would be my set point for starting irrigation, or somewhere in that neighborhood. So what are some grower trends here? One would be overwatering under mulch. I know I found myself doing this because you really can't see what's going on. You can't see how wet the soil is. So using soil moisture sensors can help with that. One, it can help define the wetted volume or wetted area, and it can help with determining when the soil is actually depleted from that. So soil moisture sensors can be a real asset when we're looking at microirrigation to help with that. So some resource lists. One, Netafim, which is one of the manufacturers that makes tubing from Israel, has a really nice set of online training for people that want some more information. And then I put a list of resources up that's a Word document on the Barnett UW site, which you may find helpful. Here's a list of some of the major manufacturers if you're looking for sites that may be helpful. So with that, I'll take questions. We got a lot of people on here today, so if you could type your question in, I'll try to answer that. Any questions? Otherwise, this is the last of our sessions. All these sessions are recorded and on Learn at UW under your content tabs, but eventually we're going to have them on, we've got a irrigation website with UW, and eventually we'll have them on that site as well.